Okay, so this is kind of the best because we can just hop right in. Okay, so where we ended off last time was on problem 1.7. So we're going to try to keep doing those. All right, so let's just get this going. All right. So we're starting off with 1.7. Okay, so what we want to do is we want to give, okay, so 1.7. Give state the of NFA, and we might have a little bit of overlap. Okay, so for A, we want the language A such that W ends in 0, 0. And we want 3 states. So the way that we're going to do this is, first we're just going to draw 3 states. So what I think it's going to be is like this. So you can, hang out around here for a while, computing whatever you want. But then at any point, you can branch on these zeros. And if you have any path to this point, then you're good. So I'm pretty sure that this is correct. And I think we actually looked at the answer and it was correct. B is the language of 1.6C. All right. Contains 0101 Sipser. And it needs 5 states. Okay. So for this one, I think it might be the same, except 1, 2, 3, 4, 5. I think it's just going to be 0, 1, 0, 1, 0, 1, 0, 1. Because what this is saying is that this NFA can bumble around here for a while, but it's going to keep branching on each time you get a 0, but it might die. Like, let's say on a branch of a computation, we have a 0, 0, but we decide to go this way first. We go this way, then we try to go this way, but we die. So that branch of the computation fails. But on the 0, 0, we could stay here. So we could go 0, 0, or we could go 0, 0, and then maybe the 1, 0, 1 is after that. So this seems like it does exactly what we think it should do, meaning compute this language, compute the contains 0101 as a substring, and it has 5 states in its NFA. Okay, problem C is 1.6L, which is even number of zeros or exactly 2 ones. Okay, so let's think about how we're going to do that. So we need an NFA. Oh, and how many states? 6 states. Okay. So let's just look at the DFA. For the DFA for even number of the zeros is going to be like this. You're going to start here. If you, and this is an accept state. And if you get a 0, then you go to the odd case. If you get another 0, you go back. But on both of these, you can get 1s. Okay, so this is the DFA for even 0. Then exactly 2 1s is going to be, you start here. If you get a 1, you go to another state. If you get another 1, you go to another state. But if you get another 1, you go to this dead state. Okay, but the NFA that does either of these, what we could do is we could add a state here, add an epsilon here. So this, though, would have 3. This would have 7 states, not 6 states. Now, this is an interesting question, actually. If let's say we had the NFA like this, we had a 1, and a 0, 0, 0. I believe that this actually works because even if you're in this accept state and you get another 1, your branch of the computation dies, so you can't consider it to have accepted. So I think that this is all we need. So we're just going to go 1, 2, 3. You go 1, 1. You can have as many zeros as you want. That's fine. So this is my answer. Because if you have no arrow to follow, then you can't consider it to accept. So I think that this is right. Okay. All right. The language A is equal just to the set 0, 2 states. So I think that this is literally just, I think it's just that. Because if you get a 1, it dies because it has nowhere to go. If you get a 0, it's good, but if you get anything else, it dies. Reach the end of the notebook. 70 pages of math, baby. It's okay, I came prepared. Yeah, check something really quickly, though. So what are we on? We're on 1.7, 1.7e, which is A is equal to the language of 0 star 1 star 0 plus 3 states. Okay, so we're going to start off probably with just a 0 here. Then you need a 0 here, actually. You can't, if you're used to the DFAs, you would kind of think you want a 1 there, but you don't want a 1 there. Because then you require that you have at least 1, 1. Well, even here. No, you know what? You need an epsilon here. And then here, you do your 0. Because this plus, 0 plus is equal to 0, 0 star. So, oops, can't really see that. Okay, so this is the accept state, and you can have a 0 here. Okay, so this language says that you can have 0 or more 1s, or 0s, then 0 or more 1s, and then 1 or more 0s. So here, this first thing, you have 0 or more 0s, because you can just run on that. But then at any point, you can epsilon transition over to the second state and try to add some 1s. Finally, at some point, if you get a 0, you can transfer over to here. Okay. We are now on 1.7F. I think I did this one last night. So this is going to be A is equal to 1 star 0, 0, 1 plus star 3 states. Okay, so the first thing that is immediate is, let's just draw the 3 states. So this thing is going to have a 1 here. And then I think you're just going to do this. 0, 0, 1. And then this is an accept state. So notice, since there's stars on both elements of the concatenation at the top level, that means that the epsilon string works. In addition, we also have that the just a string of 1s works. But then finally we can go 1, 1, 1, staying here. And then we do 0, 0, 1. And we can just keep taking that path as many times as we want. And it doesn't accept anything else, because the only thing going out of here, or let's say this one, is a 0. So the only thing that could follow that 0 is another 0. Otherwise, that branch of the computation would die. Excuse me. Okay, G. This is going to be A is equal to this. And so I believe that this is, and it says with 1 state. All right, so if we have the language that consists only of the empty string, then we're going to have just a single state here that's an accept state. There's no transitions or anything. There's no arrows at all, except for this little start arrow. And so if it tries to do anything but be the empty string, it's going to fail. And I think they went over this in the book, but if you had A is equal to the empty set, so equal to empty set, then it would be this, where even if you have the epsilon string, give it an empty string, it still is not an accept state. So that's the difference between the set of the epsilon and then, oh, that's the next one, is it? Oh, no, it's not. Okay. So now 1.7H is 0 star A, the language A is equal to 0 star 1 state. I mean, I think we know what this is. This one's pretty easy. This is an accept state, and it has a 0 here, and that's it. Okay, so we did 1.7. Nice. Okay, now I tried to do these last night. 1.8 is actually pretty hard, I think. So 1.8, we'll just go over here. So use the construction in the proof of theorem 1.45. I'm just going to go here really quickly. To give state diagrams of the NFAs recognizing the union of languages described in 1.6a and b. So what we want to do is we want to make an NFA that does this and does this. So, and let's just quickly go over to 1.45. Okay, so here was the proof idea of how to stitch NFAs together. You basically add in one more new state that is the start state of the union, and you add epsilon transitions to there, and then you just let them proceed as before. Okay, so 1.6a and b. So take, or let's say build NFA union of, let's just switch back over here. So we're going to build the union of A, or let's say A1 is equal to the language W. W starts with 1, ends with 0. And A2 is equal to W, so I said W contains at least 3 1s. Okay, so let's just build the DFAs again. So A1's DFA is going to be, so if you get a 1, let's see if we can do it with an NFA. I think you can do this. I think that this works. So that's the first NFA. Then A2. See, okay, here's what's weird to me about A2. Counting finite automaton, it's like, don't you have to just make it a DFA? Because it's like, okay, you have a 0 here, you can do as many zeros as you want, but when you get a 1, because you can't remove these arrows. So anyways, at this point, you can then do this. But this is a DFA. That's the thing that's weird to me. Is I don't know how you can make it an NFA. I mean, of course, every DFA is an NFA. I'm just saying, I don't know how you could write it more simply than this. But in any case, then the union, A1 union A2, we're going to have this. We're going to add a new state. Then we're going to add an epsilon arrow. And really, we don't need to do, well, we don't need to rewrite it. Here's what I'm going to do. I'm just going to say epsilon to here. And epsilon to here. And that's really all we have to do. So now let's try to run let's just okay, so let's try to run one that accepts in only exactly one of them. So this one, we're just going to give the string 1, 0. So it's going to go here, it's going to go here, then it's going to branch. Well, first off, okay, branches to both of these. It can also stay here, but that we're going to see that that immediately dies, so we can kind of ignore that one. But so, all right, so we're testing the string 0, 1. So first off, let's say 1, 2, 3, 4, 5, 6, 7, 8. So let's say we're in state 1, and we get the epsilon string. Now we're in state 2 and 5. Okay, and then in our computation, we have the string 0. So our test string is 0, 1. So we get a 0. Or wait, no, sorry, 1, 0, 1, 0. So this is a 1. So we're going to get this guy can go only to 3. Then 5 can go only to 6. Okay, so we still have exactly 2 branches of the computation. Now we get a 0. Okay, now 3 can go either to 3 or 4. And this, we'll put a circle around it for accept. Okay, and then 6 can only go to 6. So what we ended with is sort of 3 branches of computation, state 3, state 4, and state 6. And we're at the end of the string, and one of them was an accept state. Therefore, this computation, or this NFA on the string 1, 0 accepts. All right. Okay. 1.8, we're now going to take the union of, so 1.8, take NFA union of 1.6C and 1.6F. Okay, I'll be right back. Yeah. So we probably have like 45 minutes left. All right. So we're going to take the union of 1.6C and 1.6F. So okay, so A1 is equal to 1.6C. Okay, contains, all right, so W contains 0, 1, 0, 1. Okay, then A2 was F. F is, doesn't contain. Okay. So it's going to accept if either of these are true, not if both of them are true. So W contains, so we built an NFA for this one already. This was going to be the, it's like this, 0, 1, 0, 1, 0, 1, and then 0, 1. So this is A1's NFA. Okay, then doesn't contain 1, 1, 0. We can just do this. Oh, this is the accept. So what we're going to do for A2 is we're going to do the exact same thing. 0, 1. Oh, wait, actually, we need to think about this, but let's try to proceed assuming that because we know that for DFAs, if you basically take the complement of the accept states, then you kind of negate this clause. So if we build the DFA that says the set of strings that contain 110, then if we flip all the states, then we get the negation. But it's not clear that if you do that with a DFA or with an NFA that you can actually do that, and it still is the negation of the language. Okay, let's proceed as before. So we're gonna get 1, 1, 0, 0, 1. So if we made this the accept state, then we would get but so what we want to do is we want to take this, this, and this. But let me think. So let's try to give it. Okay, so what we'll do is we'll give it 1, 1, 0 as the input, and then we'll just see if there's any way. See, because look, if we go 1, 1, then it dies. But if we go 1, 1, 0, see, that's not going to work because this path alone can compute and accepts everything. So we can't do that. This is definitely not right. How would you do it as a DFA, though? I think what you do is I think you go like, okay, you can start off with as many zeros as, okay, so what we're going to do is this is going to be A2 complement as a DFA, So if you start here and you can do as many zeros as you want, but once you get a 1, you go over here and you're sort of like starting off assuming that, but if you get a 0, you're going to go back to here. If you get a 1, you're like continuing on. And if you get a 0, then you're in the accept state. Okay, but if you get a 1 here, then you want to go back to this. So now if you go 1, 1, 0, but now let's say you go 1, 1, 1, oh wait, 1, 1, 1, you don't go here, you go here. So now you go 1, 1, 1, 0. Now if you go 1, 0, 1, 1, 0, okay. So I think that this is the DFA. So what we could do is we could just so let's play around with that. So if we negate this, so we go 1, 2, 3, 4, but we make these the accepts. Go here, 0, 1, 0, 1, 1, 0. So now because this is deterministic, we can just follow exactly where it's going to go. So if we get 1, 1, 0, then we're in the non-accept state. If we go, let's try it, 1, 1, 1, 0, 1, 1, 1, 0, because this has it as a substring. So this is the DFA. This is still the DFA, but it works. But it's clear, though, that you can't take an NFA. But actually, are we even sure that... Okay, so if we were to... So this is the NFA that I thought, where you just take the complement. But if we try to make the NFA that contains 110, then we would do the same thing as we did for the first one. So let's imagine that this is the accept state and these are non. So then you can compute around here for as long as you want, but when you get a 1, you have the option to branch over here, and if you use that branch, if you get another one, you can go here, right? You're still pedaling around here, but you actually get 2 branches because this second one is going to go there, and then finally if you get the 0, then and then that branch can do whatever it wants for the rest of time, but it's still going to be an accept state in the complement. And but yeah, so I mean, it's a good note. This shows that for language L, that you can take what am I trying to say? The complement of the DFA accept states, but not if the FA is an NFA. All right, that's fine. I mean, since we have a DFA, it really doesn't matter, I think. So then what we'll do is for the union A1, union A2, we can just use the DFA. I don't think that there's any issue with that. So, so we have epsilon transition to here, 0, 1, 0, 1, 0, 1, 0, 1. And then this is going to be excuse me. Oh, and then here, once you have it as a substring, you can just stay there. So then this is a 1, this is a 0, and this is a 0, 1, and then these are all both accept states. So I think it's right, but I'm gonna double check to see. How do you create? This was F. How do you? So I mean that is kind of a big. Whoa, this diagram is terrible. So they just gave a DFA as well. I mean, how cool is this? We can just plot it. Oh. Oh, but I don't think it can use libraries. That's why it's annoying. Oh, what a clean. Yeah, what a great can I copy image? All right, I'm not going to waste time on this. Obviously it's wrong. But it is true that you can't just do the complement thing. All right, so let's move on. I'm going to assume that my thing is correct because it does seem like this will compute the right thing. If you go here and you get it, you hang around here for as long as you want. But if there's even if if you get a 0, 1, 0, 1, you're going to end up here in some branch of the computation. And for here, yeah, so I think that this is right. We can move on. Okay, 1.9. Give A1 concatenated with A2. Okay, so A is 1.6G concatenated with 1.6I. Okay, so this is A1. So A1 is 1.6G. W is at the length of W is less than or equal to 5. So the length of W is at most 5. And then A2, 1.6I, every odd position is a 1. Okay, so how are we going to do this? So the first one, I mean, for A1, is it not just going to be 1, 2, 3, 4, 5, 6, 7? This way, 0, 1, 0, 1, 0, 1, 0, 1. Okay, so here there's 1, so let's call this the 0 state. Wait, that's confusing. All right, but okay, W must be at least length 1 to get to this point. Then 2, then 3, then 4, then 5, then 6, and then here. And then all of these are going to be accept states then. All right, so okay, so this is what we have so far, right? So basically you can do whatever you want, but you're going to keep moving down the line. But once you cross 1, 2, 3, 4, 5 transitions, then your length must be greater than 5. I don't know how you do this with a... Oh, you know what you could do? I think you can eliminate one state by the NFA version. You just get rid of this, and you add no exiting arrows here. I think that that's what you do. So this is like the... Yeah, so it's the DFA requires one more state than the NFA, but I mean, in reality, if you wanted to like do the power set construction, you'd have like 32 states. So in any case, um, okay, so A2 is every odd position is a 1. Okay, so 1, 0, 1. I think this is it, right? So you go on a 1, then you take anything you want here. If you get a 0 right now, though, then you die. Oh, but the thing is, I think that this is also an accept state for the NFA. All right, so let's try that. So let's do 1, 0, 1. So first off, the epsilon string, since there's nothing in there that accepts, then you do 1, 0, 1. But let's do just 1, 0. 1, 0. I mean, this is true because every odd position is a 1. So that's good. So now we want to give A1 before A2. It's kind of funny because the way you say this composition thing is after, but they reverse the... Anyways, not a big deal. So, okay, so for doing concatenation, I think what you do is you just take the accept states here and you add epsilon transitions to the start state. So we're going to remove these as accept states and we're just going to add like an epsilon along each of these ones, and we're going to pretend that they're not accept states. You know, you get the idea. All right, I'll be right back. Okay, so I think we did this one, right? I think we're good with 1.9. 1.9a. Let's see. B and M next. So I guess this is equal to, all except states of A1 get epsilon arrows to start of A2. And I think that if we switch over to this, that is what we do. And then, and then I guess remove except states of A1. Okay. All right, so we can move on to the next one now. Okay, I don't think we want to do 1.9b. I think we get the idea of 1.9b. Let's go to 1.10. Okay. 1.10, give a star. So we're going to give the star of the language, and then A is for 1.6b. So this is, so in 1.6b, we have the contains at least 3 ones. So, so the first thing we're going to do, so we're going to have, wait. No, we're going to have this. No. I did this wrong. So when you do a star, oh my gosh, this is terrible. When you do a star, this is what you do. So you add a new state, you make it an accept state, you add an epsilon transition to the original start state, and then for each accept state, you add an epsilon transition to the old start state. So we need to remember what the DFA that we had was for this language. And I'm pretty sure that contains at least 3 ones. It's just like, so this is the DFA. If you can get a 0, 1, 1, 1, 0, 1, 0, 0. Okay, so then all we have to do, and then this is the accept state, right? So then what we do is we add a new state that's an accept state. We add an epsilon to here, and then we add an epsilon to here. What's up, Riley? So I'm pretty sure that that's all we have to do. Let's try one more, because I feel like I don't know about that one. I have to go in like 5 minutes. Okay, so 1.10b is a star of 1.6j. Contains at least 2 zeros and at most 1 1. Which is, so A is equal to at least 2 0 and at most 1 or 1 1. Okay. So all right, so let me think about this really quickly. So if you get if you get a 1, and then you get another 1. So this is one of these lattice ones, right? Where it's like 0. So if you get 2 1s, oh, and then similarly, this one. Oh wait, this isn't gonna work. If you get a 1 here, see, this doesn't work because if you, yeah. Okay, but we know what the construction is. I don't know if we need to do this one. Let's move on. Okay. The next one's a proof problem, which I think is cool. It's kind of a cop-out to skip this one, but I mean, we know, like, whatever that DFA is, you just take the accept states and you add epsilon transitions to the old start state. Because I think you have to have, like, all right, so let's just do it. So A1, which is at least 2, 0. We're gonna have a DFA, and we're gonna say, no, we're just gonna do the Cartesian product construction. It's like at least 2, 0. Okay, so you start here, you get a 0, 1, 0, 1. 0, 1. This is all it is. And then A2, if you get a 1 and then you get another 1, then you're trapped forever. But here you get a 0. You can do a 0 here. So anyways, what you do is you take the Cartesian product of these two things. And since it's an and, you're going to have exactly one accept state because there's only one in each of them. So, okay, so we at least spelled out how you're going to do it. You're going to take the Cartesian product of this, and then you're going to add one extra state. Then you're going to make the new state that you just added an accept state. You're going to add an epsilon transition, and it's going to be the start state, and you're going to add an epsilon transition to the old start state. Then for this pair in the Cartesian product, you're going to add an epsilon transition to the the start state of just the Cartesian product without the new start state. Okay. All right. So this one's going to be prove that any NFA can be converted to an equivalent that has exactly one accept state. Okay, this proof is actually super straightforward. So basically, what you need to do is take, so let's say that n is equal to the NFA. So Q, sigma, delta, let's just say S for start and F for finish. Okay. What you're going to do is you're going to say n prime is equal to Q plus this new state A. Sigma stays the same. Delta prime S and then A. Okay, and then all you're going to do is you're going to say delta prime of I guess it's going to say F sigma. So this is really like a Cartesian product of possibilities. So it's like delta of anything in the accept state with anything in the sigma state. What am I trying to say? What we're going to say is for each F in F, add delta prime of F epsilon is equal to A. So you're just going to add epsilon transitions. In other words, add epsilon arrows to A from each accept state. Okay, what's the next one? We'll just read the next one. I probably won't be able to. Okay, yeah, I have to go. Should have zoomed in a little bit more. Okay. All right. 1 hour stream. I was hoping to do more, but oh well.